This is lecture number 29 of the course ME314 Fluid Mechanics 2, and this is the second lecture of the week. In the last lecture we already have talked about using the order analysis. We have reduced our governing equations into simplified form, which we call it boundary layer governing equations. Today we will go into that content. We are interested in the boundary layer over a flat plate, and we will solve it analytically, and that solution is called as Blasius solution. Using that Blasius solution, we will be able to work out the wall shear stress as well as the friction coefficient, and in the end we will solve problems using that Blasius solution. We know there is a flat plate and the fluid is approaching with uniform velocity. We call it a free stream velocity, and once in the region close to the plate where the viscous effects are dominant and the velocity, there is a certain velocity profile develops which would be a function of space coordinates here if it is a steady state problem, and we can see that this is the boundary layer thickness that grows as we move along the length of the flat plate. So what Prandtl has done in 1908, Prandtl proposed that the fluid flow can be analyzed by dividing into two regions. One is this inviscid flow region where the viscous effect is not dominant, and the region which is very much close to the wall, we call it a boundary layer region where velocity gradients are significant and viscous effects are important. So that region would be the boundary layer region. So what we do here is from an experiment, what people have done over the flat plate. X is a different position over the flat plate. Once you are at 1 centimeter or 2 centimeter, X describes the position. So what one of the student of the Blasius Hansen has produced a plot where on the y-axis you have dimensionless velocity, where u infinity is the free stream velocity over the flat plate, which in this particular problem we have taken it as 8 meters per second, and u is the local velocity. And on the horizontal axis we have plotted a parameter which is some sort of dimensionless distance from y and x, and the term in the bracket looks like close to the Reynolds number. So Hansen plotted that experimentally at different positions of x, and what we see is this is a typical plot of that velocity distribution. And what we can do is what Blasius has done. Blasius has put that velocity, dimensionless velocity, which is u over u infinity, would be some function of y over delta, and delta we call it a boundary layer thickness. And from our order analysis we already have seen that the boundary layer thickness delta would be some function of x. So at this point what we can do is we can have some velocity profile which would be some function of y and delta. So y is here, and the delta I just substitute the delta here. So this becomes a new variable. I call it a similarity variable eta, which is basically some function of y over delta, and we can write like this. Our fluid flow is governed by the governing equations, and we know that from in the boundary layer we have a simplified governing equations. This one is a continuity equation This one is x momentum equation, and you already know that delta is a boundary layer thickness which is much smaller than the characteristic length. Where in our case it is the flat plate, so the length of the flat plate is the characteristic length. So using that order analysis, we end up with that governing equations, and we know that the boundary conditions, in order we need boundary conditions to solve such governing equations. So the first and the prime boundary condition is at the wall, what we call it a no slip boundary condition. So velocity component u and v would be 0 when y is 0. So once you are at the wall, there is no motion of the fluid layer. And another boundary condition is whenever your y is such that you go into the free stream where your velocity is approaching towards the free stream velocity. So in that case, when your local velocity is approaching the free stream velocity, you say your y is somewhat equal to your boundary layer thickness delta. What Blasius has actually done is Blasius assumed that there is a velocity profile, and this is in this dimensionless form. It would be some this dimensionless velocity would be some function of the dimensionless number, what you call it, y over delta. Y is an arbitrary value from the wall, any value of y, and delta is the boundary layer thickness when your y is such that your local velocity u approaches towards the free stream velocity. So from our knowledge of the scale analysis, we know the order of the boundary layer thickness is delta, which is much smaller than the characteristic length, and we have introduced here similarity variable eta, and if we relate that single variable eta with some stream function, so we already know from our potential flow knowledge that stream function, if you know the stream function, by differentiating the stream function you will be able to get the velocity components. So this is what we will do it here. For example, the u component of the velocity can be worked out if you differentiate that stream function with respect to y. So what we have done is we have invented a similarity variable eta in such a manner which is there is some mathematical function which is represented by that we have stream function. So once we know that stream function, we can easily work out those velocity components. So let's see here, if let's say I know that stream function psi, so if I differentiate with respect to y that stream function, I am going to get the u component of the velocity. So just to bring f eta and the term in the denominator on the in this side and differentiate psi with respect to y. So here you see you are differentiating with respect to y. So u infinity x and kinematic viscosity would be considered as a constant. So but as I know that this term eta is some function of y and x both, so I apply here the product rule. So once you know the u into v, so u derivative of v, let's say this is u, this is v, u derivative of v plus v and derivative of u. So instead of writing down f eta, I am just simply writing f, because I know f is some function of a similarity variable eta. So v u derivative of v plus v derivative of u, and the whole thing is, as I know, is no more changes with y. So it is a function of x here. U infinity is a constant, nu is a constant, so the derivative of that thing would be 0 here. So u would be equal to this term times how partial derivative of that function with respect to y, So what I have done is, and the whole term is whatever the function is, if multiplied by the 0 is going to get 0. Here what I have done is f with respect to y can be written in terms of applying the chain rule. So this is exactly because eta and eta cancel out, and so it would be the same thing as dava f by dava y. So I have just used at this point we have used this the so-called chain rule here. Okay, now I know that u is some function of f is u is this term. I have reproduced again. Okay, and this thing is, as I know that eta with respect to y, so I know how eta relates with y from that equation. So this equation relates how eta relates with y. So if I differentiate eta with respect to y, I am going to get this term in this square root. So this is what I got it if I differentiated eta with respect to y. I got the term in the square root. So okay, now I have and df by deta in a shorter notation. I can write the f prime, and you know, this nu x and nu x cancels out, and under root u infinity and under root u infinity becomes u infinity. So I have got u is u infinity times the first derivative of the function f, which I am using it with the notation f prime. Once I have worked out u component of the velocity, now I can work out the y component of the velocity, which is differentiating psi with respect to x. I am going to get the negative v component of the velocity. So here I know that stream function, so now I differentiate with respect to x, and obviously the next step is again taking the product rule, and then just simplify the expression, and at this place with respect to dava f with respect to x, so f with respect to x and eta cancels out, so I use the chain rule again here. And if you differentiate this whole term with respect to x, because x is a variable here, so what is constant? Nu is a constant, u infinity is a constant, under root is a constant. So root under root x would be 1 upon 2 under root x. So that would be the derivative of the root x. And since x is we have to put f with respect to this function, f is here, and this is the derivative of that function. Root x is the derivative of root x is 1 over 2 root x. Okay, and then we have to make some further simplification. I am not going into the algebra. So you work out that algebra, and you just simplify that expression, so you end up with the y component of the velocity would be some functions of eta and that f. So I know by inventing the stream function in terms of some function f, I am able to get the velocity component u and v. But as we know, in our governing equations, I need it some more. I just don't need only u and v, I need how the u changes with respect to x as well. So once I have a knowledge of u, and dava u by dava x is much simpler, just differentiate the whole thing. So now I differentiated this whole thing. Instead of with respect to x, I can bring it with respect to eta first, and then differentiate it with respect to x. So just changing the order of differentiation, and then this becomes d square f over d eta square. So it would be a second derivative of f with respect to eta. And I know that eta with respect to x, if I differentiate, I am going to get this term. So eventually I got the first derivative of u with respect to x in terms of that function f with respect to eta. So I got all these ingredients from my governing equations u, v, and dava u by dava x, and then I worked out in similar manner dava u by dava y. So differentiating u with respect to y, I got this term. So I mean, kindly do that algebra and calculus. Okay, the second order term that is required for viscous term in the governing equation is dava square u over dava y square. So it means it is a second derivative of u with respect to y. So first I have a knowledge of dava u by dava y. I just again differentiate with respect to y. So just bringing the dava u by dava y in the bracket and differentiating with respect to y, and just by changing the order I end up with the second derivative of u with respect to y. Okay, so I have now my x momentum equation, the simplified governing equation, which is supposed to be good for flat plate when your Reynolds number is high and your boundary layer thickness is much smaller than your characteristic length. So I have the ingredient u, I have the ingredient dava u by dava x, I have the ingredient v. So I just substituted all these variables in the x momentum equation. So I have the knowledge of u, I have the knowledge of v, I have the knowledge of dava u by dava x. So just put everything in that equation. I have not mentioned dava square, but that is already here. So I have just substituted all the things. I have substituted the value of u, which is u infinity times f prime, and then I substitute the value of dava u by dava x, which is this thing having d square f by d square is second derivative in the double prime. I have used the simplified notation, and then plus, and the value of v is substituted here, which is the whole thing, and then v is multiplied by dava u by dava y, and I know dava u by dava y is this thing, would be equal to kinematic viscosity times the second dava square u by dava y square term. The whole term is substituted here. Okay, so what I am able to do it in that equation after substituting all these u's and v's and their partial derivatives, first order and second order, I end up with an equation which is not having any partial derivative. So during that similarity variable, I am lucky in a process that I have simplified first and then further simplify. This u square infinity over x cancels out. So what I end up with a differential equation which is third order ordinary differential equation. So f, as I know that f is only a function of eta. So df by d eta I am working out, so f is only a function of eta. So here instead of x and y variable, by using that similarity variable and converting it into some stream function and then calculating the velocity component and the velocity gradient, we are in a position to transform this partial differential into ordinary differential equation. The point is this is ordinary differential equation is also a non-linear differential equation, and its closed form solution or analytical solution is still not possible. So what Blasius has done, Blasius has obtained the solution of that equation which satisfy that equation, the twice of the third derivative of that function plus the function times its second derivative. The results end up with 0. So this equation is satisfied using the series expansion. This is what the Blasius has done. This partial ordinary differential he has solved using the series solution. And let's see how the solution looks like. So you have the boundary conditions available and the variables involved. We know that this dimensionless velocity is some function of y over delta, and we know there is an eta variable which is some function of y over delta, because the y is already there and this thing is the delta, or this thing is an order of delta actually. So the solution looks like represented in this form, where eta is this variable and this is the function of that variable, and at that value of eta it is the first derivative and it is the second derivative. So as the eta is changing, the function, its first derivative and its second order term is so these are those possible solutions for that ordinary differential equation. And let's check out at the boundary condition. What happens is, at our boundary condition, when your eta is 0, so eta is 0 only when your y is 0. So when you substitute your y is 0, your eta is 0. So what you are going to get, your at eta 0 your function is 0, as well as your u is also 0. So first derivative is nothing, u over u infinity. So once u is 0, then the first derivative is also 0. So here the first derivative is also 0 when your eta is 0. So it means that solution is at least satisfying this boundary condition, the so-called no slip boundary condition. So that has been shown here. For its that is being this function, if plotted with respect to the eta variable, so once eta is 0, then this function is also 0. And as we know, as eta increases, so eta increases from 0.1, 0.6 and approaches towards some value, so that your function will be approaching towards unity. And this is what the first derivative of that function. So first derivative of that function is nothing, just the first derivative is actually a dimensionless velocity, u over u infinity. And we know once u reaches to the boundary layer thickness, then u would approach towards u infinity. So your first derivative would end up to unity. So this is what you see here, when your eta increases in such a manner that your first derivative approach towards 1. So once it approaches towards 1 or unity, then we can say that your local velocity would approach towards the free stream velocity. So I mean, we are not taking unity, we already have defined that our boundary layer thickness is your delta is equal to y, because when your local velocity approaches towards the free stream velocity, or 0.99 of the free stream velocity. So u over u infinity is 0.99. It means first derivative would be 0.99. So it is 0.97, then the first derivative is 0.99 here when your eta is 5.0. So your solution is eta would be 5.0. So and we can plot these series solutions. They are shown in the table here, and here it has been plotted. So as we know that your function is increasing from 0 to onwards, so your function is increasing from 0 to 2 and it is a monotonically increasing. So the blue one is representing the function, and the brown one is representing its first derivative. So first derivative starts from 0 and going approaches towards 1 is its asymptotic function. So it is its maximum value of that function would be approached towards 1. So this would be the plot of the first derivative. And if you see the second derivative, interestingly, once your function is something like 0.5 something, 0.4 something, and then it starts decreasing, and it starts decreasing in such a manner that your eta would be approaching towards a very big number. So eta is approaching towards a big number, but your second derivative which approach towards zero. So that second derivative is approach towards zero. So this is the graphical representation of the Blasius solution. Either you use this plot or you use this table. Okay, now let's see how this Blasius solution help us in calculating the required parameters on a flat plate. So we know this represent when eta is 0, it means your y is 0. It means is y is 0, you are at the no slip boundary condition. So your u over u infinity, which is your local velocity, is also 0. So that is actually your no slip boundary condition, and this is the second boundary condition when u over u infinity approaches towards free stream velocity or 0.99 of the velocity, then your eta approach towards 5.0. So if you plot the first derivative, which is nothing a dimensionless velocity u over u infinity versus a similarity variable eta. So you see here there is the variation of velocity with respect to the free stream velocity. So obviously the maximum value of u could be equal to u infinity. When u equal to u infinity, then f prime maximum value would be 1, and corresponding to that 1 value of the first first, which is approaching not 1 but approaching towards 1, 0.999. So once you go to 0.999, your value would approach towards 5, approximately approaches towards 5. So your eta variable would be comes out to be 5. Then that vertical distance from the wall would be equal to the boundary layer thickness. So as you see, eta is our similarity variable, which is some function of y over delta, and y is this, and this thing is sort of a delta. And what I have done is I have just using the Blasius solution. What I have done is I have just substitute y equal to delta, and corresponding to y equal to delta, when your first derivative approach towards unity or 0.99, then your eta comes out to be 5.0. So instead of eta, I have just substituted 5.0. Okay, now I can simplify this expression, because as I know it is under root x. So if I multiply and divide by the same number, it does not make any difference. But what will happen is I will be in a position to write down this expression in terms of Reynolds number. So here x, if you take that out of the square root, under root x square would be x, and the whole thing would be u infinity x over nu is your Reynolds number. So what we have learned is that boundary layer thickness divided by this local distance would be 5 over square root of the Reynolds number. And if you look back of your previous lecture of order analysis, what we have done in the order analysis is the delta over x. Delta is some function of x over square root of that Reynolds number. So even without solving the governing equation, I can find out that what would be the relationship between what will be the value of the boundary layer thickness as a function of Reynolds number. But that was just a relationship. But after solving the governing equations using the Blasius solutions, I got that proportional sign into equal to sign. So I know how much would be the boundary layer thickness at every value of x at a given Reynolds number. So as we see that the boundary layer thickness grows, so delta increases, which is a function of x. So once x is 0, your boundary layer thickness is 0. When x is increasing, x increasing means you are moving along the length of the flat plate, and at a given Reynolds number, you will end up with 5 times of that x value over that Reynolds number. You will be able to get your boundary layer thickness, and as x increases, your boundary layer thickness increases. So this is how we will using that solving the governing equation, we have calculated the boundary layer thickness over a flat plate when there is a laminar flow over a flat plate. Okay, once we have worked out the boundary layer thickness, I can easily work out using the same solution the wall shear stress, because as you know, wall shear stress is how your velocity gradient changes with respect to y, and since it is a wall, it means your y would be approaching towards zero. So what I need is I have already calculated dava u by dava y. So from our previous slide, we already know what will the value of dava u by dava y. I substituted the same thing, and here y is 0. So once y is 0, your eta would be 0. So what I have done is when your eta, I just substituted eta 0 in that equation. So its second derivative term for eta would be 0.33206. So it means this term is actually 0.33206. So instead of this, I can write using that Blasius solution from this table. I can write this thing 0.33206 is my solution. So I have just substituted the solution here, and the rest is I just want it in terms of the Reynolds number, just make a simplification. So I end up with the wall shear stress, which would be 0.332 times rho free stream velocity square root of Reynolds number. So once for this laminar boundary layer, I can calculate the wall shear stress, which would be a function of Reynolds number. And so this is an advantage of this Blasius solution. I could calculate any parameter which is involving velocities. So wall shear stress involves how the velocity changes with respect to y. Similarly, I can work out the friction coefficient. Friction coefficient is nothing, the wall shear stress divided by the dynamic pressure. So I know the value of wall shear stress from the Blasius solution, just substituted the thing, and I got that friction coefficient would be 0.664 over under root Reynolds number. So we already have seen it earlier from order analysis that the friction coefficient decreases as the Reynolds number increases. So this is for laminar flow. As the Reynolds number increases, the friction coefficient decreases. And if you see the counterpart of the pipe flow problems, using the Darcy equation, small f was your Darcy friction factor. So this is small f was 64 over Reynolds number. So that was the same inverse relationship. As you increase the Reynolds number, your friction coefficient decreases. So for the external flow problems, that is the flat plate, also your friction coefficient, which is defined like by this equation, also behave in this similar manner. Okay, now let's see this problem. We have atmospheric air at a temperature, so it means that a kinematic viscosity is given at that temperature. So if in exam this kinematic viscosity is not given, then using the tables at the corresponding to 30 degrees centigrade, you can work out the kinematic viscosity, because we know viscosity is a strong function of temperature. As temperature changes, viscosity changes. So the air is moving over a flat plate which is 8 meter long, 2 meter wide, and the free stream velocity is 2 meter per second. So assuming that the laminar flow exists in the boundary layer over the entire length, and at x equal to 8 meter along the length, calculate the y component of the velocity using the Blasius solution. So what is given here, the local value of x is given, the free stream velocity is given, the kinematic viscosity is given. As I know from the knowledge of this Blasius solution, the velocity component in the y direction is v, and this v is equal to half under root this thing, and I have all the ingredients available in this square root term, and I need a knowledge of eta and df by first derivative of eta. So this is something I can easily work out, because what I have to calculate the y component when your reaches to the maximum value of y. So maximum value of y occurs your maximum velocity actually is when your local velocity approach towards the free stream velocity. So u over u infinity comes out to be unity, because you know the first derivative is u over u infinity, and this first derivative comes out to be exactly 1. So here the first derivative is exactly 1 when your eta is 8. So once your eta is 8, so I just have substituted my value of eta is 8 and the first derivative is 1, and corresponding to 8 its function would be equal to 6.27921. So I have just substituted the value of that function. So I have all the ingredients available in this equation. So I just calculate the magnitude of the y component of the velocity. So this is how you can calculate the first derivatives and all other parameters. If it says that it's a boundary layer which is a laminar, so this Blasius solution only good for the laminar boundary layer. So this is where I stop today's lecture.